Hi, my name's Robert, and this talk will be on the type system that is the main purpose of this video channel to talk about. So we have quite a few things to get through. The properties of types and how they're organized, the type hierarchy itself, how automatic conversions then work, how we turn that partial order into a lattice by adding unions and intersections that are very similar to set unions and intersections, how operators translate using this system. Then we get on to proposition types, which are very important and lead onto subset types, and then how execution works. I think that this type system, the lattice type system, gives dynamic typing a run for its money in terms of convenience for the programmer. All types have properties which are just attached named values. The names are atoms. Now, atoms are formed just with a dot and an identifier. Other things can have properties. Anything known at compile time can have a property, but that's not used. Only properties of types are currently used. Properties are defined in behaviours, which you can spell without the U if you like, and behaviours are often in indexed families. So if we consider the type, the behaviour of being a monoid, the natural numbers are a monoid with add, but they're also a monoid with multiply and with maximum. So we need to distinguish these. So we would actually be looking at monoid dot add, which means monoid itself is something that takes an atom, dot add in this case, and returns a behaviour. All right. So we write that in my language, something like monoid.add equals a behaviour of type. As I said, you can have behaviours of different things, but we're interested in behaviours of types. So that will be a recurring thing here. It extends semigroup, so it's just got a little bit of extra added on to semigroup. We then provide a procedure that takes a type. It'll be the type that we're considering giving this behavior to, and returns a type. The return type is what's called a structure, which you would be wise to have seen my previous video to understand. But you'll probably get the message from the next slide. And then once we've got this thing, this behavior, we can declare, for example, that the natural numbers conform to monoid.add by, and in that case, we have to provide, the structure is a type, and we have to provide a value of that type. For example, we'll define the operation and the identity, which is the feature of the monoid, and the laws that it has to obey. So types are going to either be primitive or they're going to be implemented using some other type. The correct way to use them is with their defining behavior. However, they will also have implementations. So primitive types have behaviors that match the compiler target, whatever we're trying to aim at, and they have behaviors that are defined in the manual, as it were, of that compiler target. But ordinary types have a behavior that uniquely defines them, and they can then have implementations that implement that behavior. It turns out that it's not always easy. We'll show you the natural numbers in the next slide, I think, that have a well-known defining behavior. But it's not always easy to do. A way of solving this problem is often to add a property that's an embedding into another type, and that makes your that makes your definition and the unique. There's only one type that can behave that way. And of course, that's quite likely to be the same as the implementation embedding for some types. All right, so here's an example. We had to have a defining behavior. In this case, it's called nat define because it's going to define the natural numbers. It's a behavior of type, all that we're only interested in behaviors of types. It extends equality, and more needs to be said about equality someday. And as I say, it's a type goes to type. Now, the only type it's going to be applied to is actually the natural numbers because that's the only thing that matches these properties. So we'll spec the input. The input, as those who've seen the previous video know, the input of a procedure is $. So we just set that to we set the name nat to be $, because that's the only thing that's going to be passed to it. And so we might as well for ease of understanding. And the property, the behavior that we need to define the natural numbers, we need a 0, which is a natural number. We need a successor function, and that's actually an embedding. So the successor goes from a number to the next number up. But you can also go backwards. Now, the going forwards always works, so that's total, but going backwards fails, specifically when the natural number is 0, because there's no, it's not the successor of anything. And in fact, we need to have a type, and this is a proposition type, and we might come back to look at it after we've talked about proposition types, but it says that there's a type that says for all natural numbers, because there's a proof that the successor of $, is not equal to 0. So the successor of the input, give it any natural number, and the successor of that number is not 0. And there's another one called induct, which is allows for induction, and you can do a huge amount with that. Now, that's once again a for all, and it's for all natural numbers go to type. So for all propositions, which we call this proposition P, if we've got P of 0 and P of any number implies P of the successor, then we can deduce that P of any natural number is true. So that's just normal induction. And then we can create, once we've got our behavior, we can define the natural numbers with a new type operator. So humans are used to subtyping. A dog is also a mammal, an integer is also a rational, a group is also a monoid. This is normal, and what I want to do is to add subtyping in a way that's uncontroversial. So we do this by adding, in the first instance, adding is a declaration. So that's an embedding of the lower type into the higher. So we can say, we might think it's a good idea to say that an int is a rational, and what we supply then is an embedding function. So it's from int to rational, and the $//1 is just the normal way of operator that creates a rational number. So it's $, divided by 1, in other words. $, is the numerator and 1 is the denominator. Now, so we get a collection of these. We can even have 0 of them, because we'll still end up with unions and intersections of types. But there are actually many cases where we will want to define is-a declarations. We add the obvious, an X is an X, and if an X is a Y and a Y is a Z, then X is a Z. This is called transitive closure. So we do the transitive closure of all our ISA declarations, and then we end up with a partial order. What makes all this work is that in addition to their own properties in their own behavior, types inherit properties from above. So ints are rational, and rational has a dot denominator property. Then int does too. Int dot denominator, but is still just a rational goes to nat. It doesn't have to. Properties don't have to say anything about the thing that they're a property of. So in situations where the lower and the higher type have a common property, then they're required to be compatible. So int and rational both have an addition property from monoid, as we talked about, but their answers are compatible in an obvious sense, but it actually needs to be well defined what that means. So here's an example to show you how it all fits together. So suppose we have this situation. We have a dog is a mammal, a dog is a quadruped, a crocodile is a quadruped, a human is a mammal, and mammals are animals and quadrupeds are animals. So we get some various diamonds in here. They all have to commute. So if a dog goes up to if we push a dog up to be an animal, it doesn't matter which way we go. That's important to make subtyping work the way humans expect. And as we just mentioned, there will be a pair of procedures. So dog will go to animal, and there'll be another one that always succeeds, and animal goes to dog, but that might fail. Of course, the animal goes to dog comes down by a mammal or comes down by a quadruped, and it doesn't matter which way you go, you might have to get the same answer. We turn this into a lattice, an order lattice, as opposed to a lattice that's like a tiling of the plane or something like that. A repeating system is also called a lattice, to be confusing, but this is a lattice that's a certain type of partial order. And make it a lattice, we need to have a least upper bound for any set of the things that we're doing. So there's going to be a least upper bound of mammal and quadruped. That will be the union of the two things that are either one or the other. And that, because it's the least upper bound, it must be lower than animal, which is another upper bound. So so we can go up from that union to animal. Similarly, the intersection of mammal and quadruped, how is that defined to be? Well, the values of it come from the values of the union of dog and cat, because they were the only things that were below both mammal and quadruped. So they're the values. However, the intersection can have less properties. As we go up, the number of properties has to go down, and the union of dog and cat could have extra properties besides the ones that it gets from mammal and quadruped. It could have ones that if both dog and cat are below pet as well, for example, then it might inherit properties from pet, like the owner, and they would be a property of, because they're a property of dog and cat, they're also a property of union of dog and cat, but they won't be a property of the intersection of mammal and quadruped. Far away the most common thing in real life is that unions and intersections are of things that are, one is already above the other. If X is a Y, then the union of X and Y is Y, and if the intersection of X and Y is X. How is equality defined in a union, and by implication in an intersection, as you'll see? All right, if they come from the same lower type, then that's no problem. We just look at the equality in that lower type. But otherwise, we try to convert both to the intersection of the two types. Of course, if they don't have any intersection, they can't be equal. But if it succeeds, if we succeed in getting them down to the intersection of two types, then we can use the equality for that intersection type. But the trouble is, the values of the intersection type, as we just mentioned before, is the union of all the types that are below all the types of the intersection. And equality of the intersection is defined to be the equality in that union. So we're actually go back to the top. But infinite regress is not possible because we only have a finite number of is-a declarations. Most intersections are empty or the lower of two types, so there's no big deal. Okay, so now I said animal is above the union, but how does that actually work? Well, the way it works is that you go down from the union to one or the other, and you must be able to do one or the other because the thing is actually one or the other, or both. Anyway, so we go down, and if both links succeed, then they have to be equal in the intersection. And it doesn't matter which one is equal, since they'll then be equal in the animal. So the union has the properties of animal, but not any of the other properties of mammal and quadruped, as we mentioned before. Okay, so this is actually a bounded lattice, which just means that all sets have a least upper bound, not just finite sets. And that includes the empty set. Now, if you think about it, the less things there are in the union, the smaller it gets. And if you take the union of the empty set of types, that would be the lowest possible type. And it's the type empty, which has no value. And all sets have a greater lower bound, and that's the intersection of the empty set. Well, the less things you have in an intersection, the bigger it is. And if you have the intersection of nothing at all, that's the highest possible type. That's type any. So any has all values at the top, and empty has all properties and no values down at the bottom. So values at runtime and expressions at compile time automatically convert to higher types when required, which, as we mentioned, always succeeds. Downward conversion happens only when it's explicitly required, but they can fail. These are simple cases. There's actually a general rule, which both of them are cases of, which is you go down to the intersection, and that can fail, and then you go up to the destination. We also allow conversions, which I call ad hoc conversions, defined by an X converts to Y. This is only allowed if the intersection is empty, because otherwise there'd be two conversion properties, which would be confusing. So an assignable is like an ordinary variable that can change, and it's commonly useful to have that convert automatically to the thing it's a variable of. So we want a variable integer to convert to an integer by taking the current value out of the variable box. However, you have to be careful. It only applies when X is definitely needed. So how are operators implemented in Wombat 2? Well, we use the hierarchy. And here's an example of a hierarchy that we might find useful. So integers down the bottom. An integer can be a rational number just by making the denominator 1. It can also be a complex int, which is sometimes called a Gaussian int, which by having a 0 imaginary part. And higher up, there's complex rational numbers where the real and the imaginary part are both rational numbers. So we usually go up from rational to a complex rational by making the imaginary part 0. We go up from a complex int to a complex rational by dividing by 1 again, or by making the denominator 1 again. And in between, there is the union of rational and complex int, which does have properties which are below complex rational. So what we do is we translate, suppose we're adding a rational and a complex integer. How can we do that? The obvious thing to do is to do it in the complex rational space. And what we actually do is we do it in the union, which will move it up necessarily. So we get the union of the type of X and the type of Y, and we pick out the monoid.add operation, and we apply it to X and Y. Now, since we've zoomed up to complex rational, because union doesn't have any properties except those it gets from above, and what's above is complex rational. So we get the complex rational add, and then X, if X is rational, it converts up to complex rational. If Y is complex integer, it converts up to complex rational, and then the addition can take place up there. Anyway, this is the way these things go. Of course, a more common case is that the two types are in some direct relation. So if you add an int to a rational, of course, the int gets converted up to rational, and the addition gets done there, which is what one would hope. All right, types can have the same property as we've seen, but if they have the same name and the same behavior. If they're equal, there's no problem. But types can also be combinable, and particular procedures are combinable as they don't contradict each other where they're both defined. Then the definition just gets extended to cover both input types. And this occurs in a lot of different situations. For example, it's how we can define factorial by saying factorial of 0 is 1 and factorial of n is some function. Having two definitions of factorial, they get combined. We have ordinary Boolean operators. With an appended question mark, they return the left operand or fail. This is a commonly useful thing. And this one constrains the identifiers. So equals is short for equals equals question mark, and x equals 42 sets x, or checks that x is 42 if it's already been set. With an appended percentage, they create a type representing the proposition. This takes quite a bit of getting used to, but 1 less than %3 and 3 less than %1, they're just types. There's no question of them failing or anything. They always create a type. It's the value of this type is a witness to the truth of the proposition. So, of course, 3 less %1 is empty. We prove a proposition by constructing a value of the type, and this could be hard. So we can construct a proposition that represents Fermat's theorem, but the proof might go for hundreds of pages. Universal qualifiers take a t-proc parameter. So, for example, here's one that's true for all. So it says int goes to type. So for all integers, that integer is less than that integer plus 1. We could have written successor, of course. And similarly, there exists a unique integer such that that integer plus itself equals 8. And but the fact that the exclamation mark means it's unique, and that means that a proof of that, a value of that type, has to provide a value, but also prove that all other values do not satisfy the negation of that property. So now that we have these tools, we can extend our type hierarchy with subset types. That just uses a slash operator, so some type slash a procedure. The procedure must be, or coerce to, the type that we're subsetting to type. And of course, the output type is going to be one of these proposition types. And if it's not empty, it has a witness, then the value is in the subset type. So here's an example: int slash $mod2, the input to this procedure, is equal to 0. That's the even integers. So why do we do this complicated thing of creating a procedure, creating a type representing the proposition and requiring that a value be found for that type? This allows us to deal with subsets where there isn't a general known algorithm. You might be able to prove particular things are in the set or particular things aren't in the set. And going the other way, for things that have a Boolean algorithm, that converts into a proof very easily. All right, just a word on how execution works in Wombat 2, and it uses the type hierarchy. So every expression starts out with an unknown type or type any, and the various things that happen in the program constrain the values of those expressions. So we move it down the hierarchy, and eventually in a normal way we want them constrained to a subset type with just one value. Now they might get constrained to a subset type with 0 values. That's how expression evaluation fails. It's really only if that causes an effect to be unable to proceed that the program execution fails. Okay, now for the miracle, the empty list miracle. Sometimes things turn out so beautifully that you know you're on the right track. So let's consider an explicit list. 3, the string XOXO and the rational number 7 over 2. What is the type of that? Well, the answer is it's a list of the union of the constituent types. So we've got a string and we've got rational numbers because 3 is a rational number. So putting nat, 3 is a natural number, and we're putting nat into our list in the union would give the same union. We eliminate things that are below some other thing. So it's the type of the union of the constituents, and for an empty list, the union is empty. So it's the list of the union of the empty list. But the union of the empty list is the type empty with no values. So the type of the empty list is list of empty. Now, the fact that it's a list of something that has no values doesn't matter because it doesn't have any values. And for all types, empty is an X because empty is at the bottom of the hierarchy. So if empty is an X, then list empty is a list X. That's the standard library thing. So that empty list thing, left square bracket, right square bracket, converts to list X for any X, which is just what you want. And it's so much nicer than all the other things where there's languages where there's hand wavy things saying, oh, the empty list is what sort of list you want at that particular point. Okay, so there's a lot more to say in future videos, including how types are implemented, solving the problem of evil. The problem of evil is where equal values give different results, and it's a very important problem to solve in my language. How to construct general proofs by dealing with terms, and introspection to make proofs about expressions, including programs, and there's a whole lot more. Stay tuned, and I'll see you in the next one.